So thanks, Professor Taobi, Dr. Min Liu, and Professor Guang Chen for the kind invitation. And it is my great honor to join this our event sensor fusion workshop to introduce something about our work on a hybrid image fusing, neuromorphic, and conventional cameras. I'm Boxin from Peking University. So actually, the concept of neuromorphic vision is not new, but it becomes useful, or we can record the data to realize the neuromorphic vision. And thanks to Professor Taobi's great contribution to the DVS or the follow-up DAVIS sensors since the year of 2005 or 2008. And actually, people know that event camera or the DVS is a kind of one of the most popular examples of the neuromorphic camera. It triggers event at a time when a single pixel sees a change in the brightness larger than a threshold. And yeah, for the first commercialized version in 2008 under the name of DVS, we can use this type of camera to record the fast moving, like this throwing a ball, this kind of motion by detecting the increasement or the decreasement of the brightness changes in this kind of red and green pixels. So actually for today's talk, I'm introducing something about the complementary mechanism between the conventional and also the neuromorphic sensors. So in part one, I will briefly introduce how we can use images or conventional images for better events. And in the second part, I will introduce something about the other side. We can use events for better imaging. So due to the limited time, I will focus on more on the recent works maybe published by our group in this year, like in ECCV 22. And for other early works, I will just very quickly go through the basic ideas and the quick results. So actually, one of our first papers in this kind of joint filtering mechanism between the images and neuromorphic events appears in the CVPR 2020 and a later version in TPAMI 2021. So at that time, we noticed that both the frame-based cameras and the event-based cameras, they have very nice complementary properties. Like for the event-based cameras, they have very high speed, high dynamic range, but frame-based cameras have been used for so many years and they have much higher resolution and it could become less noisy. So why don't we just combine this kind of strong properties from each other, and then to achieve this kind of even higher for the noise robust imaging with higher resolution. So we try to build a prototype, what we call the hybrid system and the RGB-DAVIS dataset. It's quite simple prototype. We just use the beam splitter to synchronize the two types of cameras. When the light comes in, it gets splitted and it comes to two cameras simultaneously. So we can use this type of simple prototype to capture what we call the RGB-DAVIS dataset. On the left side, you see the images. On the right side, you will see how it is synchronized. The events comes along with these images. So when we have this kind of data, we can do this kind of computational framework, what we call the guided event filtering. But because we have two modalities of data, and we can use one type of data to guide each other to increase the quality of one. In this work, we use images. It could be high resolution. It has colors. So it can guide the event generation to be in a higher resolution and become less noisy. I will skip the detail of how we compute it just to show one quick result. This is a real data we use our prototype to capture because we have a lake in our university campus and there is a bird there. So you can see that the raw event data could be very noisy and flickering around. But when we conduct this kind of joint filtering, we can super resolve the data to 8 times higher resolution and it becomes less noisy. But here comes a problem. If you see the video, actually the RGB video quality is very good. But sometimes if the RGB are with conventional video or images, they are in good quality. Why do we still need an event camera? So event camera, it outperforms when there is a fast motion, when there's a higher dynamic range. So we start to think, so if we don't have the RGB images with good quality, can we still try to denoise and super resolve the neuromorphic events? But to us, the inside, something similar to the ISP for a conventional camera, what happens inside the event camera is still, at that time, is an open problem to us. So we try to ignore that. So we try to capture the screen. When the screen, it displays images in different resolutions, and we can capture them for the corresponding events in different resolutions. And we can try to learn by building some 3D unit architecture to learn the mapping from the low resolution noisy event data to the high resolution one. So it could achieve some result like this, what we call the event zoom. This is a very typical example when you have a checkerboard moving around, and the data we expect is like what we show on the right side. It has very clear edges for the blue one and for the red one, but the raw event data could be very noisy. And this is what we have learned to denoise and super resolve the images just from the noisy event data. And there's another fundamental problem when we try to link these two modalities of data, what we call the data association problem, which will appear in this year's ECCV 2022. When we have the event camera and when we have one intensity camera, we can put these two types of cameras in arbitrary poses. We can use a larger baseline, one, for example, one on this side, one on the other side. Then we can move them together and try to do some online estimation for the camera poses. And also we can put it side by side like the stereo setup used for this kind of small baseline for depth estimation. But then there is a key fundamental problem to answer is how can we connect these two types of data? This is like what you can establish for two images using the safety features. But now we have two modalities of data. Then in this work, what we want to solve the data association problem is to, at the subpixel level, to make their correspondence quite clear. So we propose to use transformer modules, making the features more distinguishable. And there's a two-stage architecture according to some properties of the event streams. And we try to estimate for both the large and the small baseline to achieve the state-of-art performance for the pose estimation and depth estimation without requiring the history of camera poses. So this is our computational framework. We have two type of cameras they can in different baseline, and we have the event streams and also we have intensity images. What we used pre-process event stream is an existing representation called the time surface. Then we have this kind of FPN. It means a feature pyramid network to process these two types of data to extract the coarse level and also the fine level features. What we have the L sparse net here. This L stands for large, meaning that for this network we have the larger receptive field to try to calculate the correlation matrix between these two types of data. And the output is this kind of our mutual nearest information. And based on this, we can conduct a small baseline, a small receptive field operation, what we call this S stands for small dense network, to predict based on the mutual nearest from the previous output to have this kind of post estimation. In order to get the per pixel depth estimation, we have another dense prediction layer there. Then after combining all this together, we have a two-stage transformer-based architecture to really establish the kind of data association information. It could be used for post estimation, where we have this kind of in subpixel level pixel correspondence between the event data as well as the intensity data. And of course, we can do the depth prediction, depth estimation based on that. So this is what we show how we can use images to enhance the quality or extract more information from the events. But we know that events have very nice properties for probably to break the bottleneck of existing cameras for higher dynamic range, for motion, for very fast motion without blur, right? So in the following works, we also try to extract how we can use event data to guide the image reconstruction problem. So this is our ICCV paper, what we use event to get the APS frame from the DAVIS camera. We know the good properties of the APS from the DAVIS camera. It outputs both event and also the APS. It's actually our low resolution, low dynamic range, and the kind of blur grayscale images in a little bit lower resolution. But this information is very important because we have two types of data synchronized, very well synchronized on the same chip, right? So, and also we have a lot of redundant information from the event stream, at least in the time domain, it's much faster. So can we explore the redundant information from the time domain to try to increase the quality of the APS frame, to conduct the super resolution as well as denoise for this kind of APS frame to make it higher resolution, higher dynamic range, and with sharp edges. So there are actually many existing works try to do this kind of enhancement, but we try to formulate the problem from a different manner that is based on multi-image super resolution, because we thought that one is relatively well-posed problem. This is also because we have the redundant temporal information from the event streams. Let's say when we have the event volume, it could be very fast, but we have a reference frame, which is the I hat here. And then for the event volume, we can just divide it into different parts, like I denoted here, the E-1, E+1, and so on. And take the E+1, for example. We have the I as a reference frame here. And from the event information, we can calculate the intensity residue and add it back to the I hat to reconstruct a latent frame, which we call L+1, which corresponding to the APS or the intensity information corresponding to this part of the volume part of the event information. And we can do this for L-1, +2, -2, and as well. Then by using one APS frame, as well as a set of the a segment of the event volume, then we can reconstruct multiple latent images. Then we can conduct multi-image super resolution. That's how we convert or extract the redundant temporal information from the event streams into the reconstruction process of the latent frames, and then to super resolve and to upsample the original APS frame. Then if the idea is clear, then network design and processing method could be very simple. We have the LFR network, which is used to do this kind of latent frame recovery or the reconstruction. And based on that, we can do the multi-image fusion. This is just some deep learning version of the multi-image super resolution. And here is one example of data using the 4x super resolution on the real data. And here you can see how our super resolved results with clear edges and much more information here. And based on that work in this year, ECCV 2022, we further proposed the neural event stack. This is a neural-based event representation, specially designed for event-based image enhancement. The motivation here is pretty much similar to the previous work for enhanced or the super resolved of the APS frame. We just want to combine these two types of information, and also even want to reduce the domain gap between the two modalities of data. But the key to solve this problem is a proper event representation. There are actually many previous works on event-based representation as a pre-processing for the event, because we need to fit them to the network to somehow to together with the images to process them, right? We can use very simple some handcrafted representations such as event stack, time surface, or even voxel grid. But they are widely used in image enhancement. But the problem is that it could be noise sensitive because the handcrafted features, they just stack them together. The noise are also there. And there are also event-based representations for high-level vision tasks, such as the phased LSTM, matrix LSTM. They are good for high-level tasks, but they do not consider the properties or the information we need for event-based image formation model. So the problem formulation for this work is pretty much similar to the previous one, that we still look at the different segments of the event volumes. And we want to use this kind of residue information and add it back to the original or the APS reference frame to reconstruct the latent frames. We can separate them into different segments and then do the event integration together. And this is how a blurred, low resolution, the APS frame is formed, right? But here we want to do the multi-image super resolution based on that to get the super resolved result with much higher resolution. But here we find that the relationship of the two latent frames bridged by the corresponding events, because they have this kind of relationship. So the ill-positiveness nature of this problem actually can be relieved by integrating both the images and the event to achieve this kind of image enhancement. Here is one interesting observation, is that we find this kind of our process contains two parts. One is the volume part. Let's say I0 is sometime, and this is something happened before it. And we have the preceding part. This is a time that is larger than that. But for when we're integrating the events, or there is one property of the event camera that is less explored by previous papers, that actually the threshold it is a spatial and also a temporal varying property. If we look at it from different directions for both the preceding and also the following part, actually they have different thresholds. But existing representations, they do not consider this kind of information. So here we want to include this kind of bidirectional information into the event processing stage. That is what we proposed, called the neural event stack. We designed this kind of nest, we call it nest estimator, to encode both the preceding and the following events separately. Here, it contains a feature or extraction block here, and consisting of multiple dense convolutional layers to perform this kind of local event feature extraction. But the key is that we have both this direction and that direction for the blue one and the orange one. These are some bidirectional conv-LTS block to construct what we call the nest. Nest is here. This is our sub event volumes. And then this is the latent frame numbers of all the reconstructed latent frames. This not only encodes the temporal information on line in events, but also fills the spatial information and reconstruct the gradient information by this kind of our convolutional operation. So what we call the nest is after this network. There are some high dimensional features that learned from this process. And then when we have this kind of nest representation, it could be very useful in some event-guided image enhancement tasks. For example, for the blur, since we have both useful information, the local, there's kind of spatially varying properties encoded in this kind of event stacks, neural event stacks. Then the following network could be very simple. For example, for the deblur, we just use a very simple UNet, and for different slices of the nest, then we get the output. This is result on the real data. We compare with some other end-to-end event-based image enhancement method, and also we try to replace representation with other existing ones. And our experiment proves that using nest, we can get the best visual quality for this kind of recovered result. And for the super resolution, it could be also very simple. So the SNet is some RGB blocks, and then we have this our original input image bilinearly interpolated, and then with the SNet result, when we combine them together, we get the super result. All the network design can be quite simple because of the rich information encoded in the pre-processing stage. And this again are some comparison with other representations. And then combine these two types of deblur and also the super result together, and extended in the temporal domain, we can do the high frame rate video regeneration by simply from the events and also the APS frame, we get high quality video. And also in this year CVPR, we find it very interesting to use the event cameras to try to correct the rolling shutter effects. This is often observed on very cheap CMOS sensors because of this kind of row by row exposure. And when we capture this kind of highly fast-moving scenes, you will observe this kind of distorted edges. When we find the event information are thanks to the nice properties from the DVS camera, it is not distorted. It has two nice properties. Actually, it accurately records the motion information, and also because of row by row readout mechanism, some part of the information get included, but the event information if the event camera can record this type of hidden information, which is not visible by the conventional cameras. Here is a toy example to demonstrate what has been lost by the conventional camera. When the blocks move towards each other in different directions, you will see that some of the information is occluded. This is a rolling shutter image, this is a global shutter. So when you read out at this time, so this green information cannot be recorded by the sensor, by the rolling shutter sensor, and also the edge get distorted. I will skip the equations here, but actually the event helps to recover this kind of hidden occluded information, and also helps to establish the correct motion correspondence between these two types of data. Then we, based on these two observations, one is we want to synthesize based to get back the occluded part, and the other part is we want to use the correct motion information recorded in advance to undistort the edges. And other just some refined, quite simple refined deblur modules. I will skip them. And we use a very high-speed frame-based camera to record the data, to synthesize the event, and using a hybrid system similar to our previous work to record the data. And here are some results on the real data. By the end of my talk, I will very quickly to introduce another type of camera, which is invented and made in our Peking University, what we call the spike camera. So for a pixel, the difference is that for the light intensity, it's kind of accumulated. And for the event camera, it's a differentiated manner. If the accumulated intent reaches the dispatch threshold, then a spike is fired and accumulator is reset. So we just have the 1, 0, 1, 0. What we call it VIDA. It's kind of Vira radar. It's proposed by Peking in 2018. It can record the texture information like 40K frames per second. So it's easier to reconstruct the images compared to the differentiable manner. And based on this kind of sensor and this kind of new type of cameras, we have not only my own group, there are many professors in our big labs that are conducting research on this area. We have the classification, detection, optical flow, reconstruction, simulator, and many works on this kind of spike vision models and algorithms. And we release some of them open data and even open source code. So if you are interested in more about another type of neuromorphic camera, if you have interested, please take a look at some relevant papers on spike-based vision. And here is actually in today's talk, I mainly introduce how we combine the neuromorphic and conventional imaging in a complementary manner. This is part of the research direction in the camera intelligence lab at Peking University. And here is our lab's website. If you are more interested in other directions in our lab, please feel free to visit our website. Okay, thank you. And I'm ready to take questions.